let's go ahead and start.
Okay. Well, welcome everybody. Good afternoon, good morning, wherever you happen to be, to our third session in our Analyzing ACS Data with R and Python. This is a series sponsored by the Social Science Data Analysis Network at the University of Michigan. I'm Bill Fry. I'm associated with the center. And we're very pleased again to have Kyle Walker, the expert on all these kind of issues, with us today. Today, talking about using geographical data and making maps in Python. Those of you who have been with us all along have been in our first two sessions, 2 weeks ago, introducing using ACS data with R. Last week, looking at mapping and spatial analysis with R. And now we're going to be looking at Python. We're trying to be at the cutting edge of analyzing census and American Community Survey data with these new techniques. And Kyle Walker is absolutely the top guy to talk about them. And we're so pleased to have them as part of our webinar series. He's Associate Professor of Geography at Texas Christian University, and he's its director for the Center for Urban Studies there. He is well known for writing about this, consulting about this kind of stuff. And I should say, and I hope he says a little more about it, he's just come out with a book called Analyzing US Census Data, Methods, Maps, and Models in R, which is just out. You can get it on Amazon and other places. But we're very pleased to have him today. He is going to be, this is the first time we've talked about Python in our several years of doing this series, and I'm very excited to see what he has to say. And I know the large group of you who have signed on to this webinar are as well. So without any further ado, I'm going to pass it on to Kyle Walker.
All right, well, thank you so much, Bill, for the kind introduction. And thank you for all of you who have come out. And for those of you who have attended the previous two workshops and you're sticking around for the third one, or for those of you who this is your first workshop. All of the workshops are reasonably self-contained, so there will be plenty to learn today that doesn't depend on the previous two workshops. And in fact, today's topic, focusing on spatial census data and mapping in Python, is related to the previous content that we've done, but in some cases, very new. And just to kind of step through the introductions a little bit more, about me. So Bill mentioned I'm a geography professor at TCU, focusing largely in demographics and spatial data science. I consult broadly in those areas, work in a wide variety of industries, doing analytics in real estate, investment, healthcare, and I also do R and Python coaching and training. So, along with that, some of you may be familiar with some of the work I've done on the R side. I've developed a series of packages to work with spatial data and work with census data in R. And some of you may be introduced for the first time today to my first foray into package development in Python. Late last year, I released the pygris package for Python, which was a port of the tigris R package to Python. I'm excited to introduce that to you. Little bit of a plug. Again, my book is just out, Analyzing US Census Data, Methods, Maps, and Models in R. It's available from Routledge, the publisher. It's available on Amazon. And if you find these materials useful, a great way to support this work is to go pick up a copy. Even if you're coming from more of a Python background rather than an R background, I think there's a lot in there that can be learned. And in fact, a lot of the examples that I'm going to be sharing today are in fact inspired by or derived from examples in the Analyzing US Census Data book. So got all sorts of chapters in there. The first section is all about kind of just getting acquainted with decennial census and ACS data. The second section is all about GIS. So thinking about GIS and spatial data workflows in using R. And the third section is all sorts of other topics, including international census data. So for those of you who are maybe attending from outside the United States, yes, we're focusing on US specific topics here, but chapter 12 of the book, we look at data from Kenya and data from Brazil and data from Canada and other places. So hopefully there's a lot in there for you. And the reception has been really, really good so far to the book. And these workshops have been a big part of that. So I appreciate all of you coming out. So talking through the general workshop series, the SSDN staff is hard at work getting the recordings processed for the previous 2 workshops. So if you missed those workshops, those recordings will be up. We did 2 previous workshops. On the first one was 2 weeks ago on working with the new 2021 1-year and 5-year American Community Survey data with R and Tidy Census. Last week, we focused on working with those same data sets, but from a spatial standpoint, so making some maps and that kind of thing. And today is all about spatial data, spatial census data and mapping in Python. And so I'm seeing a couple questions coming through, and definitely going to get to them about how do I access the slides? How do I access the code? Wanted to make sure that we got most of the participants here before I sent that out on the chat. So what I'm going to be doing is I'm going to fire up here in just a second on the chat some links, and those links are going to be the kind of workshop material. So I'm going to talk about that in just a moment. Today's agenda. So we're organizing the workshop into 3 roughly 1-hour chunks. And, you know, if you can stick around for all 3 hours, that's fantastic. If you want to come in and out, or if you can only make the first hour, totally fine too. In the first hour, it's going to be an introduction to spatial data in Python. So for those of you who are maybe coming from a non-Python background or maybe a non-spatial background, we're going to get you up and running. This is not going to be a wholesale introduction to Python, but we're going to spend some time getting to know Python a little bit and talking through some of the vocabulary and then relating that vocabulary to working with spatial data. We will typically we'll probably go that first hour right until 2 o'clock Eastern time, and then we'll take about a 10-minute break and reconvene 10 after the hour for hour 2, which is all about finding data to map and making maps with those data sets in Python. So in the spirit of this workshop series, we'll spend a little bit of time talking about resources for finding census and American Community Survey data in Python, merging that to your spatial data and making some interesting maps. And then we'll talk about how you can use spatial census data to map other topics. In fact, we're going to go through a presidential election mapping workflow and some of the pitfalls that you'll run into when trying to make these sorts of popular maps. And I think that'll be of interest to a lot of you. And then in hour 3, we're going to focus all about GIS and spatial data analysis. So we'll be covering, I think, some more basic topics in doing GIS in Python, and then a few more advanced topics as well. So if you're coming from a total beginner background, or if you're coming from an advanced analyst background, or anything in between, I think there's going to be a lot in here that you can draw from, regardless of what perspective that you're coming from. All right, so following up and really thinking about how you get going with the workshop materials. So if you've ever attended any of my workshops before, there has been kind of a particular workflow that I like to set up, because we think about 3 kind of groups of participants that might be here. One group is going to be the power users. You already have Python installed on your computers. You know, when I say the term conda environment, you know what that means. That's going to be one group. Another group is going to be kind of the Python curious. Maybe you've heard of Python, you definitely want to try it out, but you don't necessarily know how to install it, or you don't want to mess around just yet with installing it. That's fine. And then the third group is you're curious about the topic, you'd like to learn a little bit more, but you're not necessarily ready to run the code today. All of you can benefit, and I have materials that will hopefully help. So watch the chat for me. I'm going to post some links. So the first link that I'm going to post, and then I'm going to jump over there real quick so we can take a look at it. The first link that I'm going to post is the link to the workshop GitHub repository. And the workshop GitHub repository looks like this. This is where I am storing all the materials for these workshops. So I have instructions for participating in all of the workshops. What you'll do is scroll down here and you'll look at instructions for the third Python workshop. And so I have some instructions for newer users and I have some instructions for more advanced users. And so if you are a newer user, or frankly, even advanced users might be interested in using this workflow, I've set up 3 Google Collaboratory notebooks. I'll explain what that is and give you the tour in a little bit, in which you can go in and run this code and execute it. I'm going to step you through that workflow. And in fact, I'm going to facilitate the workshop through Google Colab and explain all what that is. So you'll grab this link. I'm actually going to copy the link address and I'm going to post that into the chat. And then I'm going to go ahead and visit that link. So if you visit this link, you'll be taken to a Google Collaboratory notebook. And this is part 1, Introduction to Spatial Data in Python. I'm going to be flipping back and forth between the slides and this notebook. And I'm going to show you exactly how to use this notebook. So if you haven't used Colab before, if you haven't used Python notebooks before, don't worry about it. I'm going to step you through all of that in just a little bit. We have a separate notebook for each hour of the workshop. And I'm going to share that link. Those links are available in the GitHub repository, but I'm going to share that link at the beginning of each hour as well. And so the last bit, for those of you who want access to all of the resources, you might be interested in having the slides up on your computer. And so this next link that I'm posting to the chat, that's going to be a link to the slides themselves. So the same slides that I'm using, those are hosted on my personal website. You're welcome to pull them up. You can copy paste code over if you want, but the code is also all available for you in those notebooks. So that's the workflow that I recommend for most users. For more advanced users, so for those of you who are coming in with existing Python experience and expertise, you may already have Python and Conda installed on your computers. If so, you are welcome to clone the repository. I have instructions in the repository on how to clone it. And what I have in the repository is an environment.yaml file that you can use with the commands on the screen to build an environment that will run the code in this workshop. If all of that language doesn't make sense to you because you're new to Python, don't worry about it. You don't have to worry about that at all. But for power users who are already using Python, create a new environment. It'll take a few moments to build. And then once built, you can activate that environment. It's named ssdan-python. And then you can go ahead and inside that environment, fire up your tool of choice. I've written these workshops in Jupyter notebooks. So you'll run the command Jupyter space notebook in the workshop directory. You'll be able to access the workshop materials and run that locally. I would only recommend this for users who are already comfortable using Python and already comfortable using Conda. If you're not comfortable with that, use the hosted Colab notebooks. That is going to work, and it's going to work very well. So that's the general setup. With that in mind, let's go ahead and dive right in. So I'm going to spend a little bit of time just kind of setting things up, and then we'll jump over to the Colab notebook and get that going. So part 1 is really an introduction to spatial data, introduction to spatial data in Python. And so what we're talking about today is we're delving into Python, and I'm kind of going to frame this at the beginning for users that maybe are Python curious or new to Python. And for those of you who are more advanced, we have more advanced examples coming later. So there's going to be a lot there for you. Python is affectionately known as the second best language for everything. So there's probably a great programming language for, just about every domain, but Python is kind of is also good at it, is what the joke is. And, arguably that's true for data science as well, but honestly, a lot of Python developers would argue that Python is in fact the best language for data science. And they have a lot to stand on in that argument. Thinking here about how we're engaging with Python is through what we'll call the PyData stack for data science. You have the core Python programming language, but like other open source technologies, developers come in and they build technologies on top of that. So on top of the Python language, we have the all-important NumPy package, which implements kind of the array object. You don't need to worry about that too much, but it's the fundamental building block that allows us to do data analysis and represent data. And then we have the Jupyter ecosystem and the IPython ecosystem for interactive computing. On top of that, we have data visualization libraries like Matplotlib, Bokeh, and importantly, we have Pandas. Pandas stands for Panel Data Analysis. It's the core data analysis library in Python that allows for the representation of rectangular data frames. So kind of data that we can actually work with, sort of our data frame style. And then there are many, many domain-specific packages that sit on top of those packages. I mean, the Python ecosystem is absolutely massive and can seem a little overwhelming. So we're going to really focus that in today in what we're learning. And in fact, we're focusing on an outstanding package named GeoPandas. So if you're new to Python, GeoPandas is going to be your one-stop shop for doing GIS and working with spatial data in Python. And so Pandas is going to be your main data analysis library. For those of you coming from R, I can see a number of you are coming from the R side. The core data structure in R, the data frame, Pandas implements a form of the data frame called a data frame in Python. GeoPandas, then you can think of as analogous to the SF package in R. It provides geographic extensions to Pandas. And what's amazing about GeoPandas is that built into the package are basically, honestly, the more I explore it, I am just astounded at how many spatial data analysis and visualization tools are baked into this package. We're going to have some fun with it today. There is a whole lot that you can do with GeoPandas. So I'll give you the tour in just a little bit. What we're using GeoPandas to interact with in the very first part of this workshop is, we want to get a little bit of a tour of Python, and we're going to do so through the tiger line shapefiles. And so this workshop is about working with spatial census data. And the spatial census data that everything is built on are the tiger line shapefiles. So tiger stands for Topologically Integrated Geographic Encoding and Referencing Database. That's a mouthful. You don't necessarily need to know that. It's a fun acronym for that reason. But basically what the tiger line database is, the Census Bureau tabulates data at a lot of different geographies and maintains information about kind of the extent of a lot of different geographies. And the tiger database is sort of the canonical representation of those boundaries. And the Census Bureau then releases these files to the public as shape files, which is probably the most common spatial data format that you'll come across. And if you don't know GIS and you don't know that terminology, that's not something that we need to worry about a ton right now, but a shapefile is something that is good to know about. It's a collection of related files developed originally kind of for use with the ArcMap and Esri suite of products, but is an open standard. And so it's something that's used across different platforms. And so typically what we'll do if we're working with tiger line shapefiles is you can go to the census website, you can download a specific file, and then you can read that into your GIS of choice. And my original foray into developing packages and software for data science was several years ago when I first developed a package called pygris for R. And for those of you who have used my R packages or maybe read my book, pygris was designed to kind of simplify the process of interacting with spatial census data. I had gotten tired with the general process of going to the census website, downloading the data, loading it into my GIS. I just wanted to do that in one fell swoop. And that's what pygris allowed for. And on top of pygris, I built some other packages, most significantly Tidy Census for working with demographic data in R. But in some of my consulting engagements, I started getting more requests to work with Python. And I wanted to use a package called, or it's a suite of packages called PyCell, the Python Spatial Analysis Library, which has been around for 20 years, but is a phenomenal set of tools for doing spatial data analysis. And in turn, I found myself wishing I had kind of the ease of acquisition of spatial census data that pygris offered. I wanted that on the Python side. And so what did I do? I went and wrote pygris. Pygris is brand new, just came out last fall. And I wrote it to basically bring pygris to Python. It's a close to feature complete port of the R pygris package, and actually has a couple extra features as well. The documentation is here at this link, and if you want to pull up that documentation, we'll be adapting a lot of these examples today, but you're welcome to read through that. So let's go ahead and dive in. I'm going to show you how to get started with the Colab notebook style workflow. So I'm going to jump over here to Google Colab. What you'll see is this screen. You'll see a part 1 introduction to spatial data in Python. So how do you use all this? So Google Colab is Google's implementation of the Jupyter Notebook. And if you're not familiar with the Jupyter and IPython projects, Jupyter Notebooks were really revolutionary in data science as a way to do what's called literate programming, where you can mash up code for doing analysis or for running software and textual descriptions of what you're doing. So literate programming has become, in many ways, a widely adopted standard. If you're familiar with R Markdown or the Quarto projects, those are also examples of literate programming. And as an open source software project, we've seen lots of kind of wrappers and implementations of the Jupyter Notebook. Google's Collaboratory project is one such implementation. And a big advantage to using Google Collaboratory, I use it to teach Python here at TCU, is it integrates with your Google Drive. So if you have a Google account, you can use these resources and save them. If you don't have a Google account, you should still be able to run what you're doing, but you just won't be able to save it. So I'm assuming here that you visited this and you have a Google account and you're signed in. That's how I'm going to illustrate this workflow. I'm signed in here with an account, but an account that I did not use to author this notebook. So I'm going through the same workflow as you. What I'm going to do first and foremost is I'm going to click this button that says copy to drive. Right now, if you're doing anything in this notebook, you're working with a temporary copy of it that is kind of a mirror, so to speak, of the underlying notebook that I wrote. If you want to have your own notebook where you can make changes and save your work, click copy to drive, and it will copy it over to your Google Drive. So I'm going to do that. I'm going to click copy to drive. It'll take just a moment to refresh, and now I have this copy of part 1 intro spatial data.ipynb. You can go in and delete that, or you can put in your first or last name or whatever you want to put in. That's entirely up to you. but kind of whatever denotes it for you. And so to give you a little bit of the tour of how this works, Google Colaboratory comes with some batteries included, but not all. So there's a huge ecosystem of Python packages out there that we use. Google Colab comes pre-installed with the main packages for data science and machine learning. So I mentioned the pandas package for data analysis and the matplotlib package for data visualization. Those are already in there. And if you're doing modeling and machine learning, those packages are already installed as well. The geographic data science and the GIS packages are not pre-installed, so we need to install them. So the first thing that you're going to do here is you're going to install pygris. And we're not going to get into all of the nuts and bolts of installing packages in Python today. But in Colab, if there's a package that you need, that you want to install, you can use pip, which pip is a command that connects to what's called the Python package index. And the Python package index is one place, sort of the biggest place where developers can share their software. And so pygris is published on the Python package index, and we can install it with the command pip install. Technically, this is a command line command, and so we preface it with the exclamation mark to let the notebook know that we're using that. And then in brackets here, you'll notice I have bracketed explore. So what you can do with a Python package is you can install kind of the core package with its core dependencies, which is the software that is needed to run the basic elements of the package. I also have some optional dependencies that might be sometimes a little bit more difficult for users to configure, but we're going to be using them today. The great thing is with Colab, it'll install it just fine. So what you're going to need to do to run a cell. So our notebook, so your Jupyter notebook, in turn your Colab notebook, is organized into what we call code cells. You can see me clicking between these different cells. Those are going to be your code cells. To run a cell, you can click this little play button, or you can use the Control Enter or Shift Enter keyboard shortcuts. I'm going to go ahead and click here to run this cell. We need to install the pygris package first and foremost. This is going to take a few moments to compute. You'll notice it kind of running through, installing a bunch of different dependencies, most of which we won't interact with directly, but all of which we will be interacting with indirectly. So this should take, looks like 21 seconds to install. I'm going to click this clear output button to clear out the output because I don't need all that extra output. And now we have, now we're ready to go. All right, so how do we use pygris? How do we get started? So in Python, if you have an add-in package like pygris, it needs to be imported in to your Python session to get it to work. The import statement is how we do that. And so Python packages, you can think of Python packages as organized as a hierarchy. You have the package, which is going to be everything, and separate script files within the package are what we call modules. So those are going to be kind of different sections of your package. Within those modules are what we call functions and also classes, which we're not getting into today. But functions are going to be little bits of code that run very specific things. And so inside of pygris, there are several modules, and then there are a bunch of different functions. And if you've ever used Tigris before, pygris works in a similar way, where I've organized kind of different census data sets, so different geographies, counties, census tracts, what have you, they all get their own function. And so if I need counties, I use the counties function, and then I can specify an optional set of arguments. So for example, if I were to run this code here, I could say import pygris. That brings in the code and makes it available to my session with the prefix pygris. And then now if I ask for Python to execute pygris dot counties, it will run the counties function with any arguments that I include. And so jumping back here, to run this code, I'm going to click this button here. Sorry, I'm going to jump back to my copy. I'm going to click this run cell. And you'll notice you get a message that says using the default year of 2021. So there are a lot of different Tigerline shapefiles. Pygris supports shapefiles in some cases all the way back to 1990. And what's happening here is by executing this function, we're making a request to the census website to grab some data. We're getting the counties that we need for Nebraska because we said state equals NE. Pygris translates state and county names and postal codes, so you don't need to worry about FIPS codes or any sort of numeric codes. And then once we have that information, we can go ahead and make a little plot. This is the basic usage of pygris, pulling in those counties for Nebraska, and we've got a nice little visual representation of what we're doing. So I am going to clean up a couple tabs here so we can flip back and forth pretty well. And I want to talk through a little bit and give you a little bit of a tour of what we just did. Because if you're new to Python, there's a lot happening there that you might not necessarily have fully understood or seen. And I want to show you the type of data that we're working with and what this looks like, because this is going to underpin everything else that we're doing today. So let's get to know Python and GeoPandas a little bit. So jumping back here, I have an object, and I want to show you a little bit about how Colab works. So if you hover your cursor in between two code cells, you can add a code cell or add a text cell. And you'll notice there's even a keyboard shortcut, Control-M or Command-M on a Mac, and then B. You can use that keyboard shortcut to add a new cell if you want to. I'm going to hover my cursor here, and I'm going to add a new cell. And I just want to give you a little tour of the data that we're working with. So inside a code cell, I can execute any sort of code that I want. This is going to feel a lot like typing into an R console if you're coming from the R side of things. I'm not going to get into all the nuts and bolts of Python today, but I do want to talk through kind of what's happening here. So the object that I have here that I'm creating is called Nebraska counties. That's an object of type geodata-frame. And in this particular case, a geodata frame is going to be a special type of object in Python that has not only all of sort of the methods and attributes that are associated with a core Python pandas data frame, but also has a bunch of special geographical abilities as well. The assignment operator in Python is the equal sign. And so you'll see here me using this equal sign here. This means execute the counties function in pygris for Nebraska and assign that result to this object named Nebraska counties. So what do I get when I do Nebraska counties? I can type Nebraska counties, and then I can run the cell, just take a peek at it. And I get this printout, this big printout of what my data are. And so what you see here is, well, these are all my counties, or not all of them, but by default, if you take an object and you try to print it out in Google Colab, it'll show you the first 5 rows and it'll show you the last 5 rows. Let me talk you through what we're looking at here. All of the columns that you see, except for the last one, all of the columns are going to be the columns that are in the Tigerline shapefiles. So we have here state FP, that's your state FIPS code or Federal Information Processing Standard code, which is 31 for Nebraska. And then each county has a unique county code. We have a bunch of other information as well. The name of the county's in there. Some other related information. Maybe we have kind of a CSA or a CBSA that the county belongs to. We have land area, we have water area. Those are going to be in square meters. We have the center point or the centroid. We'll talk about that a little bit later, latitude and longitude. And then we have the all-important geometry column. What is the geometry column exactly? The geometry column is a special column that represents what we'll call the feature geometry of our data. And you can think of this as like you're playing connect the dots in a little kind of children's book, where you have a bunch of longitude and latitude coordinates. And if you were to connect those longitude and latitude coordinates, you're going to get the shape of a given county. And so what we have here is representing data as a data frame and representing data as a spatial data set that can be plotted. So methods that are available to our object, if you type the little period, you're going to see a sampling of them. So here I have all my columns that are available. A pandas data frame is organized into individual objects called series. So a pandas series is going to be one sequence of data. That's going to be like one column. And then a data frame is an organized set of series objects. But we can scroll down and you can see all of these different methods. So Python is, well, you can implement functional and object-oriented programming in Python, but a lot of Python is organized, unlike much of how R is organized, as an object-oriented language. And if that is not entirely clear to you, really what that means to you is if you're coming from R, you're going to use something called methods quite a lot. Methods are you can think of as functions that belong to a particular object. So if I wanted to kind of do something, I wouldn't necessarily, I might use a function and then pass the data object to it as the first argument. In many cases, what I'll do is I'll say something like Nebraska counties dot, and then I run a function over that. And as you can see here, there are a ton of different methods available. Some of those methods are going to belong to pandas, like the box plot method. Some of the methods are going to belong to GeoPandas, like the buffer method and the clip method. So for those of you who come from a GIS background, you can pick out a bunch of GIS methods that are already baked into all your data sets. I could buffer my data. I could run a clip operation. I could get a convex hull. I could look at the CRS or coordinate reference system, but I could also do stuff like calculate a cumulative sum. Or I could drop duplicated rows. There's so many different things that you can do, and we're only going to be scratching the surface today. A common method, and frankly, the first one I teach to my students, is the .head method. So if I run .head, I print out the first 5 rows by default. And that's just a nice way to take a peek at your data rather than having to print everything out. Another interesting thing about Colab, you see this little magic button that converts the data frame to an interactive table. If I want to, after running, say, my counties, I can click that little magic button. It'll convert it to an interactive table. It doesn't necessarily work amazing when you have geometry, but something that is nice about that interactive table format for a regular data frame, I'm going to exit out of that, is you could do a little bit of interactive exploration. Again, not optimized for the geodata frame, but there is still a whole lot that you can do with that. So that's a little bit of the tour of Python to get us acquainted. And again, there's a whole lot more that you can do. So how do we view and browse our data? Well, there are 2 main methods available in GeoPandas for plotting data. The plot method, which we've already used, makes a static map. And so if you're coming from an R background, you might be used to saying plot, use the plot function Nebraska counties. That's maybe what you're used to. Plot in GeoPandas is not a function, it's a method, which means you call the method on the object you want to plot. So if I say Nebraska _ counties .plot, I'm going to make a little plot, just a basic plot of my counties, and I can see those counties here on my screen. Alternatively, I can use the explore method, which is pretty new. It's only introduced in the GeoPandas in the last couple of years. The explore method makes an interactive browsable map of your data. So if you attended one of my previous workshops, or if you're familiar more from the R side, this is equivalent to the map view function in R. So that functionality is available natively in GeoPandas as a method. So if you run .explore over your counties, I'm going to just run that. I'm going to take a few moments to display. But what .explore does is it gives you an interactive leaflet map. And so leaflet is the most popular open source framework for interactive mapping, has been for many, many years. And leaflet is wrapped in several Python packages, but the one used by GeoPandas is called Folium. And what Explore does is it gives me now an interactive browsable map. Now, by default, a hover tooltip, which I'll show you how to disable a little bit later, a hover tooltip shows up that kind of obscures your counties a little bit and prints out by default all of the different names. But, you know, I can hover here, Sarpy County, Douglas County, and I can see all that information. I can also zoom in, I can zoom out. And it's a really, really nice way to be able to interactively display data, much like you would in a desktop GIS. So just a little view of our data there. So in terms of available geographies in pygris and kind of what we can get, data are organized by the Census Bureau along what we call the core census hierarchy. And you can think of the census hierarchy of these enumeration units as kind of two components. You have the central axis of this hierarchy, which refers to geographies that nest within one another. And what I mean by that is you start at the lowest level, which is census blocks. That's the smallest geography at which the US Census Bureau tabulates data. The parent geography of census blocks is called the block group, which is a collection of contiguous census blocks that tends to have about 800 to 2,000 people living in it. Block groups, then, their parent geography is the census tract. And then you can go up this central axis, and each of the child geographies neatly nests within the parent geography. You then have a bunch of other geographies that may be of interest to you, but they don't necessarily correspond to this core hierarchy. So zip code tabulation areas, those are going to be approximations of zip codes developed by the Census Bureau. That only fits within the nation. It doesn't fit within any other geography. You have school districts, congressional districts, you have core-based statistical areas, which you can think of as metro or micro areas. And pygris can get you all of these data sets. So they all have their separate functions that you'll use. So if you wanted to get block groups, you use the block_groups function. If you want census tracts, that's the tracts function. And over in the pygris documentation, I have a whole table of all of the geographies available and the functions that correspond to them. Inside of pygris, and inside of the census data sets, there are three types of available data sets. We've already looked at the first, which is a legal entity. A legal entity is going to be some sort of unit at which we tabulate data that also has legal significance in the United States. So a state or a county, those are actual jurisdictions with actual governments and their geographies at which we tabulate data. Statistical entities are a little different. These are special geographies created by the US Census Bureau to tabulate data, often at small areas. A great example of that is a census tract or a block group. A census tract has no legal meaning. Occasionally, it'll be drawn to approximate a neighborhood boundary, but census tracts officially have no legal meaning. In turn, they're termed statistical entities because we still tabulate data at that level. We also can get what are called geographic features in the Tigerline shapefiles, and in turn in pygris, which are other contextual geographic data sets that may be of interest. We can get roads, and the Census Bureau keeps those roads up to date. And there's a lot of contextual information in there that we might be interested in. We can get water, both linear water and area water. I'll show you how that's useful in just a little bit. So just stepping through here, an example of how we can look at geographic features. So let's take a look at roads data for Washtenaw County in Michigan, which is where University of Michigan is located. I can jump over here, and what I'm going to do is run this. I'm going to assign the result of pygris-roads, and a little bit of trivia. You always figure out where the typos are where you're developing. I've got the R assignment operator in there. It's hard to break sometimes when you're translating back and forth. You'll want an equal sign in there instead if you're copy pasting. But using the code in here, what I can do is I can create an object called Washtenaw Roads. I'm going to run that. It translates, as you can see here. So if you look at the messages, I didn't put in a year, so I get roads data for 2021. I put in MI, which gets translated to the FIPS code of 26. I put in Washtenaw, which gets translated to the FIPS code of 161. And I get this little map here, this little plot of all the roads in Washtenaw County. And I can take a look at some different properties of my data if I'm interested in. The shape attribute tells you how many rows are in your data set. So it looks like I have about 8,300 rows. And also, if I want, I can take a peek at my data using the .head method, which we already learned. So you can see there's a linear ID, there's a name. You have here the RTTYP. This will give you a road type. So I is for interstate. And the geometry you'll notice is line string, whereas the geometry above, when we looked at it, came in as polygon. So a polygon is a geography that we'll work with, which is an enclosed shape. So you need at least 3 connected points to make a polygon. The roads are represented as lines. And in this particular case, what we have here is a collection of points that form a line, but not an enclosed shape. So that's an example of what we'll call geographic features. We can also look at statistical entities. So if we want to pull tracks, we can say state equals Michigan, county equals Washtenaw, and we can grab census tracks. And there you go. So the way that pygris works in a nutshell is when you call it a pygris function, it's going to translate the arguments that you put in, and then it's going to go to the census FTP server, pull in the appropriate data set, and read that into Python as a geodata frame. It does that by default. If you want, you can use an optional argument in any pygris function called cache equals true. If you do this the first time, it'll build a cache directory on your computer for you and store the downloaded shapefile there. So in Colab, this isn't an option because, I mean, you can do it temporarily in a session, but that content's going to get recycled the next time that you use it. But if you're using this on your local computer, what you can do is you can build a cache directory, which I use all the time. It's really handy. Let's say I want to pull a block shapefile for Texas, which is about 500 megabytes. It's really, really big. I don't want to download that every time, especially if I'm on like a slow Wi-Fi network at a cafe. I just want to be able to read that right in from my computer. And so you still have to download it the first time, but any subsequent time that you use cache equals true, it just reads it in locally and it speeds up, you know, your work with data quite a lot. A few different features in pygris as we step through this. So I've mentioned the Tigerline shapefiles. The Tigerline shapefiles are great, but they represent sort of official boundaries of locations, which in Census Bureau terms, that runs 3 miles off the coastline. In many cases, you don't actually want to make plots that show 3 miles off the coastline if you're plotting counties or states. A common question that I've gotten over the years is, why does Michigan look so weird? People have gone in and downloaded Michigan from the core Tigerline dataset, and Michigan looks very strange because 3 miles off the coastline in Michigan, Michigan's basically has coastline on 3 sides of it. And so Michigan doesn't really look like people expect it to. The cartographic boundary files are maintained by the US Census Bureau for this purpose. They are pre-clipped to the US shoreline and generalized in the interior so that they have smaller file sizes, which are suitable for mapping. And you can even get kind of really low resolution shapefiles that are very, very fast if you want to do small scale mapping. So if you want to do zoomed out mapping, I'll show you how to do that a little bit later. But in this example, running this code, if you don't know all of this code just yet, don't worry about it. What this builds is a side-by-side plot that looks like this, where we can compare. I mean, again, there's your tiger line shapefile on the left-hand side. The cartographic boundary shapefile, if you're mapping Michigan, looks a whole lot better than the tiger line shapefile. So let me actually run that code through. It's going to pull these data sets down, so it's going to take a little bit of time to execute because it's pulling down two separate data sets right now. We're pulling down a counties data set from the core tiger line database, and we're pulling down a cartographic boundary counties data set as well. And then we're going to focus on Michigan. We're going to plot them side by side. And when that does get plotted out, you'll see the plot here appear in just a moment. You can really see the differences. So if you need the water area that belongs to different counties or states included, use the core tiger line shapefiles. But if you want shapefiles that are pre-clipped to the shoreline, go for the cartographic boundary shapefiles. They're often already better for mapping. So I want to finish off this first hour with a couple common use cases with functions that I solved over on the R side over the past couple years, and I wanted to bring that functionality to pygris and to Python as well. And those are kind of a couple special geometry tools that I've written that are included in pygris. So a common question that comes up when you're working with US data is, how do I represent non-contiguous parts of the country? So thinking Alaska or Hawaii or Puerto Rico, for example. By default, when you try plotting out the US, you pull down the US, well, the shapefiles are going to have these territories or these states in their appropriate geographic locations. So you end up getting maps that look like this by default, which aren't great. I'm going to run that through here, and I encourage you to do the same. I've got the continental US here. Alaska is way up here, which is where Alaska is, but the problem is part of Alaska, specifically the Aleutian Islands, cross over the 180-degree line of longitude, which means they get plotted way over here on the right-hand side of the map. And so I have all this white space here, Puerto Rico's here, Hawaii's here, and this isn't really great for doing any sort of mapping. And so a common thing that people will do in a GIS context is, if I were doing this in, say, ArcGIS Pro, I would create multiple, what we call, like, I think they're called actually data views or data frames in ArcGIS. One for the continental US, I would subset my data out. I would subset for Alaska and make an Alaska specific one, subset for Hawaii, make a Hawaii specific one, and then make a layout with a bunch of inset maps. That can be a tedious process. Sometimes you just want to automate that and make a nice looking map that shifts and optionally kind of rescales, changes the size of Alaska and Hawaii so they're more visible, or they're potentially kind of better situated for national mapping. And I wrote the shift geometry function over in Tigris to accomplish this, and I use it now all of the time, and I brought that over to pygris. So shift geometry lives in the utils module. So you see some new syntax here. I'm importing the shift geometry function directly from the utils module, and that gives me access to shift geometry without a prefix. What you can do is you can shift, so move the position of Alaska, Hawaii, and Puerto Rico to bring them closer to the continental US. And then you can optionally rescale it. So that shrinks Alaska and inflates Hawaii and Puerto Rico. Or you can try to preserve the area to show Alaska as big as it's supposed to be. So those are customized with these position and preserve area arguments. So I'll show you a couple of ways that we can do this. First things first, it runs super fast, which is great. What we've done here by using shift geometry is we move Alaska and Hawaii and Puerto Rico beneath the United States. Aleutian Islands stay together. And they're all of these are represented in a coordinate system that's appropriate for those locations. A warning, this is not the size of Alaska, not in the least bit. So don't do spatial analysis with shifted geometries. This is just for making maps. But it's really handy when you're needing to make those maps where you can do comparisons. And I'll show an example of that in just a little bit. Another configuration that you can use is, so I could say, this uses position equals below and preserve area equals false. If I switch that to position equals outside and preserve area equals true, we preserve the area of Alaska and really show how big Alaska is relative to the rest of the US. We're preserving the relative area of Hawaii and Puerto Rico as well, but we're still squeezing them closer. With position equals outside, we try to roughly represent the general kind of position in which these states and territories are located. So you have some different options that you can mash up. And so the last bit that I want to show you before we break is another use case that I originally developed on the R side and I brought in to pygris. And this is when you're mapping smaller areas commonly, even using the CB files. So in coastal areas, even when you're using the CB files, they don't always do a great job of representing water-rich areas. You'll see this in New York City, you'll see it in Seattle, you'll see it definitely in Florida. So here we're looking at Pinellas County in Florida. I'm going to run this through and take a look at census tracts for kind of the area around St. Petersburg. And yes, this makes sense. If I'm zoomed out, this is fine. I'm not going to worry about that. But if I'm zooming in, you can see here, if you look at the underlying base map, there's all this water area. Yes, we're clipping off the coastline, but there's all this water area that is still being represented as part of these polygons. So you see here, this census tract, it is represented as bordering this census tract, whereas in reality, you have water in between. And this might obscure kind of some of the actual detail that you want to show when mapping. And so the resolution that I've developed is the erase water function. What's great about erase water is it uses the area water function pygris under the hood. It fetches the appropriate water area features, so you don't have to worry about that. And then it goes in and it computes a spatial overlay and removes water area from your polygons. Let me show you what this does. So I'm going to scroll down, I'm going to run it. It's reasonably fast for, if you're running it for a specific county, it's reasonably fast to do, given that this is sometimes kind of a more complex spatial operation. And check this out now. If I'm here looking at this same area that I was discussing before, I've now clipped out, I've removed that water area, and this is showing a much more realistic representation of what those census tracts are actually like. So I use erase water all the time. If you haven't used this feature before, I certainly hope you find it useful. All right, that's the tour of pygris. So I hope you had fun playing around with it. I hope that the Colab notebooks worked well. We're going to take a 10-minute break, so we'll come back right around 2:10. Stretch your legs if you want to, or if you'd like to play around, try out these exercises. So exercise 1, try out pygris. You could, I'd suggest looking at the documentation, seeing what other geographies are available, get some different data, and try using the plot or explore methods to explore interactively. As a follow-up, if you want to, feel free to play around with shift geometry, use the different configurations, maybe the ones that we didn't try out, and see which one you like best. So I'm gonna go dark for about 10 minutes, and then we'll be back for hour 2. All right. Welcome back, everyone. What I typically like to do with these workshops, for those of you who have never attended before, is I have the Q&A up, and I will answer some of the questions directly to you as you ask. But if I see some questions that I think are relevant potentially to the entire group, then I will answer some of those live. And so first and foremost, we're getting a lot of questions about getting the slides. I'm going to post them again here to the chat. So watch the chat. There it is. Slides are available right there. And so you're welcome to use that link, and you can follow along with today's slides. A couple other questions that I found pretty interesting, that are worth addressing. So, Ari, great to hear from you, Ari. You asked, is there a Python equivalent of the question mark like you would use in R to see parameters of a method or a function? There is, and in fact, it is also the question mark, but it doesn't work exactly the same way as R. You have to put the question mark after the name of the method or the function, not before. So here in my notebook, let's say I wanted to look at the documentation for shift geometry. I could type in shift_geometry, and then I would put in a question mark in my cell. I run that cell, and what that's going to pop out is the documentation that I wrote for shift geometry. So here you can see your list of parameters. You can see descriptions of those different parameters. You can look at some notes. Here I have some credits, kind of what I was inspired by, and some warnings for working with the data. So that in and of itself is how you can get help documentation. You can also do, if you want, I can type help, use the help function, help shift geometry, and run that, and that will print out the help, not in a separate window, but rather it'll just print it out immediately, like it was an output in your Python session. And so that's another way to do it. But that's how you can grab that help documentation. Another question that I thought was interesting, is there a limit on how many polygons can be retrieved? Can I display all US Census tracts or block groups in the map? The answer is really no. There's no real limit to the number of polygons that you can get. One thing that is cool about pygris, if you want to get all census tracts or all block groups all at once, you can get it in the CV files. So in the cartographic boundary files, you can get it. And I'll show you how to do that. Like if I want all of the US tracts, I could make a new object called US tracts. I'm going to do pygris.tracts, and I'm just going to put in CV equals true. I'm not going to put in any state or any county. If I run that, it's going to take a little while to download because we're downloading a largish file from the census website. So if you're doing this workflow over and over again, it's usually a nice idea to use shapefile caching if you're working on your local computer to do that. But what this is doing is it's pulling down the full file, and for all census tracts for 2021 in the United States. And you can do this for block groups as well. You can't do it for census blocks. There isn't a national census block file that you would pull down. That would be massive. But once this executes, it took us about 40 seconds. I can look at this. Let's look at the shape. I got all 85,230 census tracts. I could plot it. I'm then plotting a lot of shapes, so I'm not actually going to do that. But I am going to take a peek at my data. And here I have every single census tract in the United States, all in one file. And I was able to get that within 40 seconds. And with caching, if I would have cached it, I could get it even faster in my next project. So those are a couple questions. Please do keep asking, and I'll address a couple other questions live at the beginning of the third hour. And I'll try to address some other questions directly as they come up as well. All right, so how do we go about kind of going to the next section? So I'm going to jump back here and I am going to pull up my workshop GitHub repository, and I'm going to need to make a new notebook. So as I said, I have taken each hour of the workshop and put that into a separate notebook. So if you want to follow along for part 2, the link is here in the GitHub repository README, but also it's in the slides. And watch the chat. There's your link to part 2. So you're going to want to pull up part 2. And part 2 is going to open up a brand new Python session. So anything that you've imported before, any variables that you've created before, that's in the other notebook. So we're starting fresh here. So I'm going to go ahead and open this up. And here's part 2, finding data and making maps in Python. Now this is very important. So first things first, I'm going to click copy to drive. That creates a copy. So here's my copy. I'm going to then, what I'm going to do right now is I'm going to close out the original version. And I'm going to rename this. I could call it like UM Workshop or whatever you want to name it, but now it's saved in your drive. And now I'm going to need to reinstall pygris because I'm opening up a brand new Python session. Importantly, what I'm doing here is I'm also upgrading matplotlib. So matplotlib is the core visualization package in Python. It is the visualization package on top of which many other visualization packages are built. We'll talk a little bit more about it, but the -- upgrade argument upgrades matplotlib. There's a feature we're going to use later in this hour that requires matplotlib version 3.3 or higher. It will not work with a version below 3.3. But Colab by default has matplotlib 3.2.2 installed. So if you want to get the code for this section of the workshop to work, and this is essential, follow these steps. First things first, run this code cell to install the packages that we need. We're installing pygris into this notebook session, and we're upgrading matplotlib, which will upgrade it to version 3.7, which will work great. So I'm booting up my Python runtime. I am doing the installation. It's going to take a little bit longer to install because we're having to update matplotlib as well. So I'm going to let that churn through. If it takes about a minute to do the update, that's about what I was getting. So we'll come back to it in just a second. And so part 2 is all about finding data and making maps in Python. And I got a couple interesting questions about if you're coming from R, would you maybe prefer to make maps in Python? You know, what is the advantage of using Python over R? You know, frankly, I tend to be a both and when it comes to different languages, and I understand, you know, a lot of us, we only have bandwidth to learn a certain set of tools. But I think as you'll see, kind of there are certain things that Python is pretty good at that you can certainly do in other tool sets. But, you know, Python has a number of advantages, you know, if you do want to go that route. And so we are going to be talking through that. Jumping back here, it looks like this installed successfully. Now, this is a critical step if you're in Colab. Otherwise, the code will not work in this section. I need you to click Runtime, Restart Runtime. So from the Runtime drop-down menu, click Restart Runtime. It'll say, are you sure? I'm going to say yes. And what that's going to do is it's going to reboot my Python, allowing Python to now use the newer version of Matplotlib. I did get one question that said, do you need to upgrade Matplotlib if you built the environment locally? You shouldn't need to do that, because the Matplotlib that's coming in, if you have built that environment, should be a more recent version of Matplotlib. In fact, I've specified that it has to be Matplotlib version 3.3 or higher that comes in when that environment gets resolved. So you only need to do this if you're using Colab. So let's talk a little bit about geographic data visualization. So with pygris, many data sets you'll work with in the United States are aggregated to census geographic areas. And so if you are working on cartographic or data visualization workflows, pygris is going to be helpful in a lot of those use cases. So thinking about shift geometry and erase water to make nice maps, well, yeah, I mean, we'll definitely use census data, and we'll use data from the American Community Survey. That's a major focus of this workshop series, but it's not the only thing that we're going to be mapping. And so we're going to look at two mapping use cases in this hour of the workshop and step you through some of the different mapping tools that are available in Python. And then really kind of think through positives and negatives to different methods of visualization. So the first use case is mapping data from the American Community Survey, which is a main focus of this workshop series. And I'll get into census data and the ACS and how we pull those resources in just a moment, but that's going to be a very, very common use case for working with pygris in Python. We will then look at a more complex example that is of extraordinary interest. So I'm hopeful that this will be helpful to you, because it's traditionally not an easy thing to do, even though it seems like it should be, and that's mapping election data. So if you're in the United States, if you're outside the United States, every 4 years, the US has a presidential election, and it is the major story in the US and a major story globally. And you'll see all of these like red and blue maps, with blue typically representing Democratic voting areas and red representing Republican voting areas. And a lot of those election maps are often misleading or sometimes not great. And we're going to step through a mapping workflow that shows, I'm not saying I'm showing here kind of the be all end all of election maps, but I'm going to show some different options that you can use to try to make your map, maybe get some inspiration of what you're doing, and make these visual representations a little bit more appropriate, all using Python tools. And you're going to learn some really cool Python tools along the way. So first things first, finding census data in Python. So I think most people who know my work know me for Tidy Census. Tidy Census is the major focus of my book. If you don't know about Tidy Census, it's an R package that I wrote and maintain that streamlines the process of working with several census data sets, like the American Community Survey primarily, and the decennial census, and census geographic data. I'm not going to write Tidy Census for Python. I have gotten this question many times. I've toyed with the idea a couple times, but that's not something that I'm going to do. Focusing my energies in other areas, in part because there are already a lot of census data resources that we can use that are pretty interesting. The thing about census data in Python, at the end of the day, just in a nutshell, especially if you didn't attend the previous two workshops, we typically go to the census website, say data.census.gov, and pull down maybe a spreadsheet of census data. And then in a typical GIS context, we'll maybe grab a Tiger shapefile, join our data together, and then do some analysis or mapping. The Census Bureau maintains something called an API, or Application Programming Interface, in which you can actually access census data sets programmatically. They have something called an API endpoint to which you can, connect to different data sets, pass different parameters, and get back so many different data options. And Tidy Census, along with a wide number of other tools, interfaces or interacts with the Census API to try to make it easier for developers working across a wide variety of languages to work with census data. So in R, there's Tidy Census, there's the Census API package, which I admire quite a lot. In Stata, there's I think Get Census package, I think it's called, if you're coming from a Stata background. In Python, there's several such API wrappers. So the one that I've used the most is called SenPy, and SenPy is maintained by some of the developers who also work on the PyCell library, who I really admire their work. And SenPy is a pretty cool library that allows you to make custom queries. It allows you to access spatial data and demographic data. The census and census data libraries are more pure wrappers to the Census API, which means they don't get spatial data. They just get the demographic data. And then I've come across recently the census dis package, which is probably the closest thing to Tidy Census on the Python side I've seen. It doesn't have a lot of users. I was the first person to star it on GitHub the other day. But it might be worth checking out. The developers put a lot of work into it. I haven't tried it yet, but it looks pretty full-featured. So there's already a ton of resources out there for doing census data in Python. So I'm not going to write Tidy Census. I'd recommend that you look at them. A couple of things about it to be mindful of. SenPy census and census data. So census data is no longer actively maintained. The developer has said he does not have time to do it. SenPy and Census, I know the developers of that are very hardworking, very busy. They have not yet updated those packages for the 2021 ACS in their core tools. There are ways to get it in SenPy, but some of their core tools don't have it yet. Census Dis, I believe, does have it, but I haven't tried that. So if you want to get 2021 ACS data, the latest ACS data, what do you do in Python? As I said, I've long admired the Census API package in R, which is developed by Honorect years ago to interact with in all of the Census Bureau APIs. Tidy Census doesn't do that. And what I have done in pygris as kind of a convenience for users who just want a Census API style interface, and they want to go grab some data and they know what they're looking for, I've written a function called get census, which is modeled after Hana's work, and allows you to basically, if you know what you're looking for in the Census API, pull in census data in very, very quickly. So you don't have to jump through any hoops to get it. And so I'm going to show you how that works. Frankly, I've talked to other Python developers about this. I envisioned it as kind of a convenience function for me that maybe others would find useful, and maybe something that if there are other developers who want to build wrappers on top of that, that could be an interesting thing to do. So let's go ahead and talk this through and show you how this works. So step one, let's say we want to make a map. Our goal here is making a map of educational attainment. So the percent of the population age 25 and up with a bachelor's degree or higher by census tract in New York City. So what I'm going to do here is I'm going to import the tracts function directly, and you can specify a list of counties. So this is a data structure we haven't used a ton yet. A list is going to be a data structure in Python that includes multiple elements separated by commas. So I'm going to say the New York City counties are New York, Bronx, Richmond, Kings, and Queens. I make a list of that, and then I can pass a list of counties to the county parameter here. So I want census tracts for 2021 for New York, for these counties from the cartographic boundary data set. So let's jump over here to our notebook and try that out and plot it out. So we're pulling that data in, you see the translation that happens, and here we have our census tracts, the CV file that are coming in from pygris. We get that very, very quickly, which is fantastic. So now what we need to do is figure out how to get some census data to join to this. I'm going to walk you through here how to use this get census function that, again, I even recommend in the documentation, if you want a more full-featured Pythonic interface to the Census API, I tend to recommend the SenPy package. But if you'd like to work within pygris and have a Census API style interface, this is in there for you. So let me talk you through how this works. Get census lives in the data module of pygris. And it has a bunch of arguments that correspond to different elements of the Census API. So in the get census function, we specify a data set. In this case, we're pulling from the American Community Survey data profile. And so in a nutshell, when we're working with the American Community Survey, what is that? So the American Community Survey is an annual survey that the US Census Bureau does that tabulates information and collects information on all sorts of demographic characteristics that might interest us. So income, education, kind of housing stock, occupation and employment, commutes, all things that are not asked in the decennial US Census. The Census Bureau then releases a series of data products. The 1-year ACS would be represented here as ACS1, and that's released every year for geographies of population 65,000 and greater. The 5-year ACS gets us data all the way down to the block group level, and it's an average, basically kind of a rolling average over a 5-year period. So here we're pulling from the ACS, the 5-year ACS, and we're pulling from the data profile, which is a data product, which is pretty fantastic. The data profile has a bunch of pre-tabulated estimates for you. So as I mentioned, what we're getting here is percent of population age 65 and up with a bachelor's degree or higher. That corresponds here to this code. And I'll show you how to look for codes in just a little bit. I specify a year. I specify kind of how I want to subset my data. So I'm asking for all tracts in New York, and the code for New York is 36. And then I have a couple optional arguments here, guess D types and return GeoID. And so on this slide, I really talk through how all this works. Data set, that's going to be the name of the data set on the Census API that you're connecting to. You want to look at this link here to see what data sets are available and how to format it. Variables can be a string or a list of strings that represent the variable IDs you want. And so for the data profile, I can go to this site here and we can take a look at it, and you get this table. And I can browse through, or I can Control F and look through to see what I want. If I wanted marital status, these are going to be the variable IDs that I'll use. So the data profile is great because there's a lot of information in there that's pre-computed. So you don't need to compute a percentage yourself. It might already be in there. And so the other parameters, year is going to be the year of your data, or the end year for a 5-year ACS sample. And then parameters, that's a dictionary of query parameters you can send to the API. Guess D types and return GeoID. These are kind of special parameters I've written to try to make it easier for joining to your data. So what guess D types does is it scans the columns and sees if it thinks that the column should be formatted as a number or as text, and then converts accordingly if so. And return GeoID, what that does is it stitches together like state, county, and tract codes to give you a column that you can join to spatial data. So let's try that out. Get census is really fast. So it's more of a low-level interface. So if you're used to tidy census is higher level. It does a lot of this stuff for you. Get census is much lower level, but it's super fast as a result. And so I can run this and I'm pulling data. I get literally in a second all the data, and I've pulled it all for the entire state of New York at the tract level. So I get that data within a second. We can take a little look at our data and see what it looks like. I'm going to do ny_college.head. And it's a pretty simple pandas data frame that is returned. I have one column that is my ACS variable of choice, and then I have a second column that is my GeoID column. And anytime that you are working in a traditional GIS workflow, you'll have your geometry data or your shape data, which is here. And I need to match that to my tabular data, which is here. And so if I look at my NYC tracks data set, I'm going to take a little peek. I see here I have a GeoID column in the tracks data set that matches the GeoID column in the college data set. To compute a merge in pandas and in turn in GeoPandas, what I'm going to do is I am going to use the .merge method. So pandas data frames have a method native to that object type that allows you to merge information from another data set to it. So what I'm doing, you can read this as, take my New York City census tracts, merge information from my college education data set to my census tracts. I specify how equals inner to do an inner merge, which means I'm only retaining matching rows. That is the default in the merge method, but I'm just being verbose about it. And then I specify an on, which means what is the column that I'm matching on. And if you're matching on columns with different names, you can do a left on and a right on in pandas. But here, both have the same name, so we're matching on GeoID. With that in hand, I can plot my data and make a choropleth map. And a choropleth map is a type of map that is using shading or colors to represent variation in numeric variable. And so in the plot method, we haven't done this yet, but as you can see, I can specify a column that'll be used to make a choropleth. I can specify if I want a legend or not. This defaults to false. I set true, and I can specify a fig size. And inside of parentheses here, which is that creates a data structure called a tuple in Python. Your first number is going to be the width of the plot, and your second number is going to be the height of the plot. So it can make it a little bit bigger. I run this through, and I get myself a map, just like that. So here's my map of educational attainment in New York. And as you can see, I mean, if you know New York, here's Manhattan. Manhattan is especially kind of Upper East, Upper West Side, Greenwich Village. Those are very highly educated areas. You have pockets here in Queens that have high levels of educational attainment, pockets in Brooklyn, Northwest Brooklyn, very high levels as well. But the map isn't perfect. There are a few things about it that I don't like. So let's talk about some options for making this better. So by default, as you can see, missing values are actually removed from the map. So it looks like we have a bunch of holes. I'd kind of like to plot those, maybe plot them with a special color to make them show up and not seem like they're just holes in the data. We have an erased water area from the map. So looking at this, okay, our census tracts are actually stretching into the Hudson and East Rivers. That is not necessarily providing the level of detail I want. This doesn't look like Manhattan in the way that I want it to look. So I might want to use erased water before I make this map. Might want to change the color palette. We're using the default Viridis color palette, which is a great palette, but maybe we want to change it. And there are a lot of palettes built in that you can choose. Also, the legend color bar is really large. We might not want the grid lines, and we don't have a plot title. So let's say we want to get rid of the coordinates, shrink the legend, which is really big, and maybe add some more contextual information as well. So let's do that. We'll use this code here. I'm going to step through it. I'm going to pull in the erase water function. I'm going to import the pyplot module of matplotlib. which allows me to do plot customization because matplotlib under the hood is being used to build these plots. And then there are a ton of arguments built into GeoPandas that I can use to customize. So here I say I want to map educational attainment with a legend with this figure size. CMap. That's the argument that allows me to change the color palette. I can use the core Veritas palettes, or I can use, if you're familiar with Color Brewer color palettes, I can use any of those as well. And so I also then can specify dictionaries of legend keywords. So if I do shrink equals 0.5, I'm shrinking the legend to half the size. And then I can specify missing keywords. So basically, what do I want the color of my missing values to be? Because by default, they're just omitted. I then specify, I assign the current plot to the ax variable, and then I can use that to turn off the axis. So let's run this through. We'll spend a little time erasing the water. Fortunately, erase water runs pretty quickly, but we are erasing over all of New York. And we get what I think is a much nicer looking map. So you can really see Manhattan here. You can see Roosevelt Island. You couldn't see that before. And you get a representation of New York City that's more realistic. And notice the area around JFK Airport and sort of the Cross Island Bridge, where there are a lot of islands that don't have much, if any, population. They were getting omitted. So it kind of looked here like the Rockaways and Coney Island were functionally detached from the rest of New York. Now we can get a better sense. Sorry, not Coney Island, but the Rockaways specifically. The Rockaways were kind of detached. Now we get a better sense of what these areas look like. So we also learned about the explore method in part 1. You can also use customization in the explore method to make really cool interactive maps. And I want to show you how this works. The syntax is similar, but not exactly the same as customizing with plot, because what plot does is it sends arguments down to matplotlib, whereas explore sends it down to folium and to leaflet. So the syntax will be a little different, but it's still pretty similar. So I can make an interactive choropleth simply by specifying a column. And by default, it's going to look like this. So just take a moment to draw the map. Now I've got an interactive browsable map with a hover tooltip. I've got a legend. I can zoom in. I can explore. There are a couple of things I still don't love about this by default. The line width of the polygons for me is too thick. And so when I zoom out, it kind of makes my map look cluttered. I don't like this big hover tooltip because when I'm trying to hover, I can't really see anything. And I want to change the color as well. So jumping back, I can specify a few things. I'm going to use this filter method in pandas. And what filter does, if you're coming from R, it's a little confusing. Filter is the equivalent of select in like dplyr in R. So what we do is we pass a list of columns we want to keep. I want to keep GeoID. I want to keep my percent with a college degree and my geometry columns. I'm going to make an object called NYC subset, and then I'm going to specify a bunch of arguments. So I'm going to turn off the tooltip with tooltip equals false. I'm going to turn on a pop-up on click with pop-up equals true. I'm going to change the underlying map tiles to one that's more muted. And then I'm going to specify some style, pop-up, and legend keywords. Once I do that, I'm going to run this through. I get what I think is a much nicer looking interactive map where the line widths are thinner. So I feel like the map comes through smoother. I can zoom in here to Manhattan. That hover tooltip doesn't show on default, but when I click on a census tract, I just get only the information in the pop-up that I need. So this is a great way to explore your data. All right, so that's a little bit of an introduction to mapping, one workflow for mapping ACS data in Python. There are lots of other ways to do it. Some of those other Python packages implement it. This is one such way to do it using pygris. In the next 15 minutes before the break, I want to walk you through another workflow where it gets more complex. And this is going to highlight some of the really interesting capabilities that not just pygris, but pandas and GeoPandas can do. And our workflow here is election mapping, a very common task that people want to accomplish when making maps, say at the state or the county level in the United States, is to map the results of elections. Our task in this 15 minutes is to make an informative county level map of the 2020 US presidential election results. So basically showing the share of the county population that voted for President Biden. That's what we're going to try to do. You might think, okay, let's just grab some county data, grab some election data, merge, make a map, just like we did before. It's not that easy, unfortunately. It's a little more complicated. And so I want to step you through a workflow here. If you don't understand everything that's happening, I wouldn't worry too much about that. Just we're going to experiment with it and walk through it. But I want to show you some of the interesting tools that are available to really accomplish an actual GIS workflow. Because this is fundamentally, here I have some raw data I want to bring in. Here I have my shapes. Doesn't work that great at first. Now I need to make some decisions around cartography. I'd like to workshop that with you. So let's step this through. What I'm going to do here is I'm going to talk you through this code over in Colab. I'm going to import the counties function from pygris, and then I'm going to import pandas with the PD prefix. So if we want to import a package or a module as something else, we can alias it. And we'll say import pandas as PD. And if you're reading in a CSV file of data, you can use this read CSV function. I saw a question earlier about, I have an external spreadsheet of data. How do I bring that in? This is how you do it. What this is doing is reading in a data set that's hosted on the web. But if you have, say, a CSV, a comma separated values file in your working directory, you can use read CSV to run that in. What I'm doing here, for purposes of time, I could have illustrated this live, but what I need to do is I want to merge my data from the county's data set on the FIPS code. And this data set, fortunately, has a column called county FIPS. Read CSV, it's going to read those county codes in as numbers. And for any of you who have ever worked with election data, census data, this is a big pitfall, because if a FIPS code gets read in as a number, the leading zeros will get dropped. So we're going to tell read CSV specifically that the D type or the column type should be object, which is the word that pandas uses for a text or a string column. There's a column in here called percent per dem for the percent voting for the Democratic candidate, which is President Biden. They come through as proportions. So I'm going to multiply that by 100 to get a percentage. Then I'm going to do the same workflow I did before. I'm going to pull my counties data. I'm going to merge. You'll note how I use left on and right on here. And then I'm going to make a plot with a red-blue color ramp. I saw one question about why the large values are light in color. That's how the Viridis palettes do it. They do the bright for more intense, and they do sort of the dark or muted for less intense. You could use a different color palette if you want to. Or, I mean, there are ways that you can reverse the palette as well. And so I'm using a red-blue color palette from Color Brewer. And so let's run this through. All right, we got an election map. It's not great. Let's talk this through a little bit. Here's my election map. In some ways, it actually works okay. It looks like some of the data processing was functional. I can see California, New Mexico, Denver, Massachusetts as blue areas. I can see the Great Plains as red areas. Hawaii's blue, that's unsurprising. Alaska is not there. No Alaska. That's a problem. We got to figure that out. And of course, there's that issue where Hawaii is way out here in the Pacific Ocean, where it actually is, but that's not so great for making an election map because I want to show Hawaii closer to the US. So on the one hand, you could say, well, we learned shift geometry. Let's use that. But that doesn't solve the missing Alaska portion. Alaska is not there. And this is where some of the practical, components of working with these data sets, this is where this comes in. So Hawaii is far away. That's a problem. Alaska is missing entirely. Why is this? Alaska doesn't tabulate votes by county. It tabulates votes by state legislative districts. So Alaska House districts. So here we have a situation in which votes are tabulated by county in other parts of the US, but in Alaska, they're not. They're tabulated in different geography. So how do we reconcile this? We need to specify a workflow. Fortunately, we can get state legislative districts in pygris. That is an available data set. So we're going to grab and clean up those legislative districts. We're going to swap out Alaska counties for Alaska state legislative districts in our data set. Then we'll run shift geometry. So let me step you through how to do this. If you don't understand all of this, that's fine. I'm going to walk you through it step by step. So at least you can get a feel for the data wrangling ecosystem available to you in Python if you want to learn a little bit more about how it works. So here's what I'm going to do. First things first, I'm going to import the state legislative districts function. And I'm going to grab state legislative districts in Alaska for the lower house from the cartographic boundary file. Next, I'm going to use some special methods for data wrangling in Python. I need to get all of the counties, but drop Alaska. The query method allows me to specify kind of a SQL query to subset my rows. And you'll notice I'm using something called method chaining. If you're coming from R, you can think of this as like a pipe-based workflow, where I say, take my US counties, then query the counties to return only those rows where the GeoID is not 02. So get rid of Alaska. Then filter my columns to return only GeoID and geometry, because I need to make sure that my columns are going to match between my counties and my legislative districts. I'm then going to take my Alaska districts and select only those columns as well, so that I have alignment. Next, I need to make a little modification. In the documentation for the election file, the GeoID or the ID column for the county FIPS for Alaska legislative districts started with 029 instead of 020. So I need to go through and replace those instances of 020 with 029. I specify n equals 1, so I'm just doing the start of the string and that's it. So if you're coming from R, this is equivalent to what you would do in the stringer package using something like str replace. Next, I use pd.concat. So that's a pandas function called concat, which stitches my data sets together. So I have my counties without Alaska. I have my legislative districts in Alaska. I stitch them together. So now I have kind of a new data set where counties in Alaska have been replaced by legislative districts. So I'm going to run that through. Just honestly takes a moment to compute. Next up, I'm going to make my map. I'm going to merge, shift, and map. So I'm going to bring in my shift geometry function. I'm going to run a merge like I did before. I'm going to shift the geometry, and then I'll make a plot that maybe looks a little bit better with a shrunken legend. It's bigger with a smaller line width. So running this through, I get this map. And lo and behold, I have an actual election map that shows geographic variations within Alaska appropriately. It has Alaska and Hawaii in viewable position. And I've got my red and blue map by county. Great, right? Well, some of you are probably trained and seasoned cartographers in the audience. This is, from a data standpoint, we've accomplished a lot here, and that's fantastic. from a visualization standpoint, there's some pitfalls to showing election data like this. The adage that comes up with every US election is land doesn't vote. And when you're using choropleth mapping, that is an inherent limitation of a choropleth map, because your eyes naturally gravitate toward those shapes that are larger and away from the shapes that are smaller, because size conveys importance. But the problem is, in the United States, the inverse is actually true if you think about contribution to the overall vote. Many of these large red counties you see here have hardly any people in them, whereas the tiny blue counties over here have a lot of people in them, sometimes millions more than there are in these red counties. But the red occupies more space because they're geographically larger. So how do we deal with that? I'm going to show you a couple methods as we close things out. One such method that we're going to take a look at is called a value by alpha map. And this is why we needed to update Matplotlib, because this wasn't possible natively with GeoPandas plotting with the old version of Matplotlib. The other solution is to not represent the votes by a choropleth map, but rather use graduated symbols, where we make the symbol size proportional to the total number of votes cast in a county, and then color the symbols relative to the percentage voting for President Biden. So let's take a look at a value by alpha map. We're going to use a special method in pandas called rank, with the argument PCT equals true, which will calculate a percentile rank between 0 and 1 for the total votes column in our election data set. And so we'll have a new column called percentile, ranges between 0 and 1. So what's great about that? We can now use that to influence the transparency of our polygons. So if you rank, say, in the first percentile, so basically you would be 0.01 is your value for percentile. So the tiniest counties in the US, you're going to have an opacity level of, you're going to be nearly transparent. We're going to put an alpha value of 0.01. Whereas if you're one of the largest counties like Los Angeles County or Harris County in Texas, you're going to have a total votes rank of like 99, which means your alpha value is going to be 0.99, and you're going to be nearly fully opaque. It's a cool little trick that we can use. So we pass that to this alpha parameter, and as of Matplotlib 3.3, you can actually pass a column to this alpha parameter and take a look at how it changes. I'm going to run this through, and we'll compare the two maps. So here I have my original map. Here's my value by alpha map. So I'm modifying the intensity or the transparency based on total votes cast. So places like Los Angeles County, the Bay Area, certainly DC, those come through very clear because these are hot, have a lot of population. In the Great Plains, look at all that bright red, but hardly anybody lives there. It's still red, but the representation is much more muted. A pitfall still is there's a lot of space occupied, and you can't get around that when you're using choropleth maps. There's still a lot of space occupied, even though the color is a little bit more muted. And so I'm going to walk you through a second workflow as we close things out here to do graduated symbol maps. And so the process is we find the center point of each county, the centroid, which is available to you in GeoPandas. It's right in there. And then we're going to use that. We're going to plot those centroids on top of a base layer of counties as a reference. And honestly, this was a lot of fun to make. And I hope you think it's kind of a cool thing to do. So I'm going to step you through what we're doing. We're going to copy our election data set. We're going to replace its geometry with the centroid. So we're converting our polygons to points. And then what I'm going to do is I'm going to create this vote scaled column that I'm going to use for the size, because I don't actually want full proportionality. I don't want some like county with 1 million people in it to have, you know, to have a circle that is maybe thousands of times larger than some of the tiny counties. I tried that at first. It basically was all a bunch of circles. You couldn't see anything. So I'm going to scale those numbers down. And then notice what I'm doing. This is a little bit new, but I'm going to establish the plot first with matplotlib. And I'm adding, using this ax parameter, I'm adding a plot of my counties as a base layer and my centroids as a graduated symbol layer. I'm adding those plots together. And then add some contextual information and run this through. And we've got, it's not perfect, but what I think is a pretty interesting map where you still see where the red and blue areas are, but those red, and you still see what circles correspond to each county, but those red circles in the plains are really, really small. The blue circles in the populated coastal areas are really, really big. And you can kind of get a sense of homogeneity and heterogeneity because we've modified the transparency of those circles as well, so that you can see the overlap. So I think this is kind of a fun way of doing it. So anyway, there's no perfect way to map elections. There are many other ways to map elections, but hopefully this provides some little tips and tricks for you working in Python. And you know, you could apply that potentially in your own projects. All right, so I'm going to go dark for 10 minutes. I'll come back about 10 after the hour, and we'll finish up with some GIS and spatial analysis work in Python. So I'm going to keep an eye on the questions in the meantime and answer a couple when I come back. All right, well, welcome back, everyone, and thank you so much to all of you. It looks like around 80% of you have stuck around for the third hour. So I really appreciate that. You taking time out of your busy schedules to, you know, spend some time, you know, with us and learn about some of these tools. So I'm going to delve in here to part 3, doing GIS and spatial data analysis in Python. Let's go ahead and get set up. There is a third notebook that you will want to get set up with. And so hopefully you have a good sense of how to do that. I'm posting it in the chat right now. So this is the link that you want. And I'm going to go ahead and grab the same. And then I want to start kind of building out the notebook. And then I'm going to answer a couple questions. So let's see here. Jump over here. So I'm going to go ahead and grab this notebook here. First things first, I'm going to do the same thing I did before. I'm going to click copy to drive. This will create a copy. And I'm going to change the name, you know, workshop part 3 analysis. That'll work. And then I'm going to go ahead and run this to install the packages. You'll notice that there are a few other packages we'll be needing for spatial analysis. This time around, we will not need to restart the runtime this time around. So that's one difference. All right, so jumping back here. Let's talk through a couple questions because I think there are some good questions here. You know, one question is someone who's Python curious, what IDE would you recommend for getting started? You mentioned Conda, but what are some benefits and drawbacks of others? So the Python universe is, it's sometimes, especially for people who are new to Python, is difficult to wrap your mind around because there's so many different ways to do things. In R has some benefits that I really like. It has a central package repository called CRAN that you install packages from, and it has an IDE, RStudio, that is frankly kind of widely used. Python is not like that. So Conda is not an IDE. Conda is a package manager. So it manages Python packages in Python environments. And so you can install stuff from Conda, and you can build Conda environments that sort of keep your packages working together. Python, as I've found, I've worked with a lot of different tools for Python over the years. Jupyter Notebooks, Jupyter Lab, which is sort of an IDE that uses Jupyter Notebooks. I've settled on, and my favorite is Microsoft's VS Code. VS Code for Python is just great. And it does everything that I really like and I want it to do. It has Jupyter Notebooks integrated. So this sort of notebook style workflow, if you want to do that, that's integrated into VS Code. It has fantastic environment management tools. And if you want to just type in a script editor instead, and send commands to an interactive window or to a command prompt, you can do that. Everything just works great. So VS Code is my favorite. If you're just starting out, Colab is great for learning. It doesn't, as you see, we keep having to reinstall the packages, so that can get tedious a little bit. But from a learning standpoint, Colab's pretty great. So when I'm teaching Python at TCU, I teach an introductory Python for data analysis course. I do use Google Colab, in part because, students already have a Google account, so they're used to using Google Drive. It feels very familiar, and a lot of this is pre-configured. So if you're really looking to level up VS Code, I think is the way to go. If you're just starting out, I would just use Google Colab like we're doing and get your feet wet. Another question about the query method. Is the query function a more preferred method for filtering on geodata as opposed to using commonly used filtering method in pandas like .loc? Please explain why .query is a preferred method. It's a great question. You'll see other methods, sort of bracket-based or label-based indexing as a way, and I'll actually show an example of that in part 3, as a way to subset your data instead of where I was using .query. Frankly, I use .query because I like it better. It works well within a method chain, and I like to do method chaining because I come from an R background, and that is how one tends to do things in the tidyverse. It doesn't necessarily mean that it's better, but I've been teaching Python now for 7 or 8 years, and I originally taught it using the traditional .loc, like bracket-based method, and students just didn't get it. It was clunky to them. They would get confused about bracket placement and how to fit different commands together. And so a couple of years ago, I switched over to the sort of method chain type methods that are in there. So filter and query and assign for creating new variables. There's a bunch of them, and comprehension improved substantially. And so I'm a believer in that kind of workflow, but it doesn't mean it's best for everybody. And so it's one of those things in open source software. There are multiple ways to come to the same conclusion. All right, with that in mind, let's dive right in. Doing GIS and spatial data analysis in Python. And so this part of the workshop, it's still, I think, going to be interesting for all of you coming from a wide variety of backgrounds. So if you're coming from a desktop GIS background, if you're coming from a traditional data analysis background, if you're coming from a maybe more advanced data science background, there's a lot of stuff in here I think that's pretty interesting. And so as we've shown already, a ton of GIS functionality is built into the geodata frame and GeoPandas, which is phenomenal. If you want to do more advanced stuff, the PySal suite of packages is just astonishingly good. It is fast. You can do so many mind-blowing things really quickly. I'm a huge fan. I just haven't used it as much in my work as I'd like because I've done so much of my work in R. And that's part of the reason, as I said, that I wanted to delve more into Python, because PySal is just so smooth. And I'm going to show you how to do some pretty interesting spatial analysis in PySal a little bit later. So in part 3 of this workshop, we're going to do a couple things. First things first, we're going to explore some common GIS tasks and GIS methods using some tools I built in pygris, but also more generally in GeoPandas. a couple pretty common use cases that you might be interested in, and then we'll do a more advanced example at the end. So we're going to do some basic stuff. We're going to do some more advanced stuff. We're going to try to solve a territory planning problem with PyCell. So territory planning is something I hear come up a lot in my consulting work and talking to people, where people say, well, I'd like to design sales territories that make sense. Or, I'm looking to develop a social service provision strategy, and I have different people I need to send out into the field. But how do I come up with kind of reasonably coherent territories so that I can have like one person who maybe specializes in this particular type of social services, like, services to the elderly, and then another territory where people are very familiar with, people who might not speak English as a first language. And I want sort of demographically coherent territories, but I don't necessarily want it to be like a collection of census tracts all over the place. They need to be geographically coherent as well. That's a hard problem to solve, but PyCell allows us to do that. And I'm going to show you an applied example of how you can solve that sort of problem. It's really, really cool in my opinion. So let's go ahead and get started and take a look at some GIS methods. There are many, many GIS methods we can do. We're just going to look at a couple, and because they tend to be pretty common use cases, and discuss what we can do with it. So first things first, let's jump in and talk about geocoding. What is geocoding exactly? If you have worked with GIS, you have done geocoding, most certainly. And frankly, when I teach geocoding, it's pretty interesting and helpful, because I can explain even to students, you've all done geocoding already. You've all done it. Anytime you type an address into Google Maps, you're geocoding. And so geocoding is the process of taking a description of a place and converting it to actual geographic coordinates that we can map, so longitude and latitude. Typically in a geocoding workflow, what we'll do is we will put in an address. Typically, we'll put in an address and we will send that address to a geocoding service. Typically, you can also build your own geocoder, but more commonly, you'll use a geocoding service. And that service will then try to figure out where that location is. And there are a variety of ways to do that. And it will give you back the location of that address as a longitude and latitude. So there are a lot of different geocoding services that we can use, one of which is maintained by the US Census Bureau. So if you're doing geocoding in the United States, you can use the Census Geocoder. And the Census Geocoder comes with advantages and disadvantages. And I definitely want to be upfront about these advantages and disadvantages. An advantage is it's free. And there's no API key required. You can just plug and play and start using it. So it is a free service. If you're doing geocoding in the United States, it's a free service. It accommodates single address lookups. It accommodates batch geocoding, which many geocoding services don't accommodate, which means that if I have, say, a table of addresses, like a CSV file or a pandas data frame, I can send all those addresses at once. The limit is 10,000 addresses at a time, and I can get back coordinates in batch. So that's really nice. Disadvantage is if you're comparing accuracy, if you need accuracy, the Census Geocoder tends to fall short compared to commercial geocoders. The Census Geocoder implements a type of geocoding called street center lines geocoding, which basically means they take that roads data set, that big roads data set that I showed you earlier, that little extract for Washtenaw County, and they take the whole roads data set for the US, and then they try to match the address. So it's basically like the address will say, let's say you're at TCU, at 2800 South University Drive, Fort Worth, Texas. It'll look in Texas, and then it'll look in Fort Worth, and then it'll look on University Drive, and then it'll look for the range, the address range, where 2800 falls, and then it'll interpolate the position. It'll try to figure out along that address range where 2800 is. may or may not be exactly where the building that is 2800 University Drive is located. It'll just put it along the street. Whereas Google and commercial providers will use a mix of rooftop and point-based geocoding and street center lines geocoding as a fallback. So Google will typically know the exact building to put the point on top of, whereas the census geocoder doesn't have any knowledge of the buildings. So it'll try to figure out along the street where it is. That is a major limitation. But I have built the census geocoding functionality into pygris for those of you who would like to use it. So if you need some of those advantages and you're okay with the disadvantages, it's a pretty nice option. So let's take a look at how it works. The geocode module has a few functions in it that you can use. So the geocode function gives you the longitude and latitude coordinates of an input census address and the census block of the address, which is pretty great. So you can parse the census block to get block group and then census tract and county if you want. I also connect to the geolookup service, and the geolookup means you can put in a longitude and latitude and it'll give you back the census block or other census information. So let's take a quick look at how this works. And I'll answer another question that I got along with that. So I'm going to clear this out. I had one question earlier that was a good one that I didn't answer. If you don't import a function directly, what does the module prefix look like? Frankly, it can look like whatever you want. It's entirely up to you. So I could do, right here, I'm importing geocode directly. And I'm going to run that through, and it gives me back this information. So where is SSDAN located? Well, it's at 426 Thompson Street, Ann Arbor, Michigan, 48106. I get a longitude and a latitude. I get the geo ID, so the block ID, and then it gives me back the address that it used for the geocoding. So going to the question, if you don't import a function directly, what does the module prefix look like? You can do whatever you want. I could do something like this. From pygris, import geocode. In this case, I'm not importing the geocode function. I'm importing the geocode module. And so I would need then to do geocode.geocode. And so in this particular case, sorry, I'm fiddling with things and it's screwing with my environment here. So I'm gonna give a little restart runtime. What I could do here, if I'm importing the geocode module, so let's try this again real quick. From pygris, import geocode. I could do that. I could also do something like import pygris.geocode as GC. I could do something like that. And then I could do, what I would need to do is like gc.geocode or that sort of thing. And it looks like I'm still having environment issues here, but there are lots of different configurations that you can do. The one thing that I am doing here is just kind of trying to make the functions bare, which is basically trying to make it a little bit easier. But maybe kind of show you, in particular. I think the distinction was better when we were doing something like, if I do import pygris, I would do something like pygris.tracks. Whereas if I did something like from pygris import tracks, I could just grab the tracks. And so that sort of thing. So I'm going to delete this cell here. This is useful, but you might also be interested in taking a look at where this location is. And so there's an argument called as GDF equals true that will return a geodata frame of the point. And so that allows us to use any of the plotting methods or the exploration methods that we've shown before. So here I'm assigning the result of geocode as GDF equals true to this variable called SSDAN, and then I can explore, and I set marker type to marker And what that does is it gives me this interactive map and plots a point on Thompson Street. Now, here's where that question I was talking to you about comes up. The SS down is housed here in this building at the Institute for Social Research. The point is plotted here, just north of the actual building, because what we're doing is we're finding along this address range. So this is going to be, there's going to be a range of addresses. This is going to be, it looks like the 400 block of Thompson Street. And so if the address range here on Thompson Street ranges from like 400 to 499, the census geocoder is going to put the point about 25% of the way along that street segment, which puts it here, even though the actual address is here. So that is the loss in accuracy that you get. A commercial geocoder like Google will put the point right on top of the building in which SSDN is located. Do you need that accuracy? Then you should go to a commercial geocoder, absolutely. Are you fine with the extra perks of using the census geocoder with that loss in accuracy? If you are, then this might be an interesting option. So that's kind of one such illustration or example of geocoding. I've also built in geocoding functionality to do custom queries inside of all of the functions, all the other functions in pygris, which is pretty cool. So let's say I want to get census tracts within 5 kilometers of SSDN. Well, this isn't a geographical hierarchy that is supported out of the box. And I don't necessarily know exactly, I'm not from Michigan, where SSDN is located. That might involve multiple counties, but I don't necessarily know what those counties are. I can use this subset by argument and pass to it here a dictionary, where the key value in the dictionary is an address, and the value in the dictionary is a buffer distance. So you can think of it as a circle that you draw around the location specified in meters. So here I'm saying, grab me census tracts in Michigan that are within 5 kilometers, a 5 kilometer straight line distance of SSDN. Let's try that out. For me, this is a pretty fun feature because this involves sort of some GIS functionality that we might not necessarily know how to do right out of the box. But now any census tract that where any part of it, and here we're getting a little shaky here, but any census tract where any part of it is within 5 kilometers of SSDN, we get that census tract back. So I'm actually, I don't know why it's shaking like that, but I'm gonna go ahead and hide that output. So that's a little bit about the geocoding functionality inside of pygris. In some cases, you want to do more formal GIS operations or find or define a different sort of spatial relationship. So what subset by does is it returns rows that intersect an input shape. So you can actually put in to an actual input shape to subset by and get back rows that intersect that shape. But you might want more fine-grained control, or you might want to do that more programmatically. And so a solution to that is something called spatial filtering, in which we'll use something called spatial predicates. And spatial predicates are built in to GeoPandas as methods. That's a lot of vocabulary. So let me bring that back and lay out a more common use case. So in census data analysis, we often want to know what census tracts fall within a metro area. For counties, that information is actually in the TigerLine file, but for census tracts, it isn't necessarily. And so we could define tracts within a metro area based on county names, but we may not know all the county names within a metro. Some metros have a lot of counties in them. And so I'm going to replicate the example given in section 7.1 of my book, in which I take the Kansas City metro area and I use spatial filtering to identify the tracts within it. So let's talk this through. We're going to need to start here, where I'm going to import pandas, import matplotlib.plyplot, and then I'm going to import the core base statistical areas function here. First things first, what I'm going to do is, and I'm actually going to split these cells. So if you want to split cells, a handy trick in Colab, if you do Control Command M and then the M dash, it'll actually split cells into two. So you'll notice I just cut these cells in half. I'm going to run this through, and I'm using something called a list comprehension. This is a little bit more advanced, but what's cool about it is it allows you to specify kind of a loop or an iterative process and then store the results in a list. So it's kind of equivalent if you're coming from the R side to what lapply or what map in the tidyverse do. So you can read this as grab census tracts for state X for each X in this list of Kansas and Missouri. Store that result in a list and then stitch them together using pandas concat. And so I can take a peek at my data. And now I have all the census tracts in Kansas, and I have all the census tracts in Missouri as well. And so if I wanted to, I could do something like ksmo tracts.plot. And you'll notice here, you'll see Kansas and Missouri. I have all the census tracts in both. And so what I want to do now is I want to identify the Kansas City metro area. I've looked this up already. I'm going to use .query to grab where the GeoID is 28140. That's the ID for Kansas City. And then I'm going to plot the metro area over census tracts in Missouri and Kansas to see what the extent is. So you can see here, there are all the tracts in Missouri and Kansas, and the red extent here, that's the extent of the Kansas City metro area. So I need to find a way to grab census tracts in here. What I'm going to do is set up some spatial filtering. You could use subset by for this in pygris, but I want to abstract this and show you how to do this spatial filtering more broadly. The intersects method will do it. It requires a little bit of extra syntax. So I'm going to run the intersects method. This basically reads as, take my Kansas and Missouri census tracts and identify for me those rows that intersect the Kansas City metro's geometry. And this .iloc0, this ends up being important. You have to index it for the first value, which Python is a zero-based indexing language. And so to get this to work, you have to add this little portion. Then what this will give you is what's called a Boolean. It's a Boolean series, which is a bunch of trues and falses. I'll show you in just a little bit. What we'll then do is use our .loc method, where we're functionally kind of going row by row and saying, okay, for those rows where our Boolean series is true, keep it. For those rows where our Boolean series is false, get rid. And then we can plot that out. So to show you real quick kind of how this works, I'm going to run this through. And I could spell this out in a little bit more, but I'm going to keep this moving for purposes of time, and then maybe we'll have a little Q&A time at the end. So you'll see here what happens. All the census tracts that intersect with a spatial predicate of intersects are retained. And intersects means that you're either falling within or you're touching the shape. And so I get all the census tracts in Kansas City, the metro area, but I also get all the ones that border it. I may be fine with that, but I may not want that as well. And so I might need to use then a different spatial predicate. What I can use is the within spatial predicate. And all of these different spatial predicates, there are a ton. And I don't have time to really get into it in more depth than that. But the within method looks and finds those rows that have at least one of their points inside of the polygon, the input polygon, but none of its points outside of it. So you have to be at least have something inside, but nothing outside. A great thing about using pygris is if you make sure that you're using the same data sets, so either the CB files on CB files or Tiger files on Tiger files, and you're using the same years, this is essential. But if you're doing that, all of these data sets are generated from the same source, so they already align with each other, which means I can cleanly get census tracts that fall within the metro area by doing this overlay process. So if I swap out intersects for within, and I'm going to jump over here and do that, I get only those census tracts that fall within the Kansas City metro area. So this is an example of how we do spatial filtering in Python. On the R side, and we talked about this a little last week, but on the R side, the equivalent method is called, or function is called st_filter. So if you're coming from the R side, this is how you do the same sort of process in Python. I do find it personally a little smoother in R than doing this in Python, but Python is still extraordinarily powerful in this regard. And here we've been able to use spatial overlay and spatial data analysis to identify a subset of census tracts that we want to use for some analysis. The last workflow that we're going to do is we're going to take these census tracts and we're going to do some territory planning in Kansas City. And I find this example really fun because it is, on the one hand, a fairly advanced example, but on the other hand, it brings together a lot of the tools that we've been learning over the course of this 3-hour workshop. And it brings us back to kind of this question that I asked at the beginning of the section. So when we're working with census data, a pretty common use case is to do territory planning. I get this question a lot from people, and I hear about it a lot because it is one of those things that is relevant to so many different domain areas and so many different industries. But on a technical standpoint, it's actually really hard. People will know what they want. They say, okay, I want to make a territory. It needs to be geographically coherent, which means it's not like a bunch of islands, unless, of course, it's literally you're working in Florida or Hawaii or places that have islands. But it's not census tracts or something that are scattered all over the place. They need to be geographically coherent. But I also want them to be demographically similar, or at least kind of demographically, meeting a certain threshold. So I don't necessarily want something where, 90% of the metro is one territory, and then you have other little singleton census tract territories. I don't want that. And, let's say, as I said before, I'm doing social services provision, or I'm doing public health planning, or I'm doing sales planning. You're going to want to, in many cases, have demographically coherent territories, where if you're looking to sell a product and you're looking to reach and market to different demographics, based on what their preferences are, you're probably going to want to be able to identify what those territories are. And let's say I make a territory in this community with these characteristics, and I'm going to want to hire a sales rep that has sort of the cultural knowledge and the domain knowledge of that community to effectively engage with customers in that sales territory. Or similarly, if you're doing, public health and doing territories for public health, and you're working for a county or a state public health agency, and you need to send kind of reps into the community to promote, say, a vaccination campaign, that would be one such use case. Well, there's going to be certain messaging that resonates in different types of demographics, different communities. And that messaging is not going to be the same. Like if you go into one community with the same sort of messaging, there are going to be all sorts of cultural factors that matter a whole lot, and all sorts of different health concerns that matter. And so you might want to make coherent territories. So this is something that I hear come up again and again, and the PySal suite of packages, just pioneered by Dr. Sergio Ray, who's at San Diego State, and his amazing team, who now are, in all sorts of positions all over the world, can do this. Specifically, we're going to use the SPOpt package, which was, I believe, originally invented by James Gabardi, who's at Oak Ridge National Laboratory now, but a number of other really talented developers have worked on it. And we're going to adapt the regionalization workflow that I discussed in section 8.5.2 of my book. But we're going to do it here for Kansas City with some different variables. So first things first, if you're doing regionalization, you have to come up with a thesis. What are the characteristics of communities that I want to sort of sift through? So you need regions that are spatially contiguous and relatively homogeneous with respect to one or more characteristics. So let's jump back and use get census and pygris to grab some variables that I've picked out here just for purposes of illustration. So we're going to use one that we've used already, which is percentage 25 and up with a bachelor's degree or higher. And then we'll grab a couple other ones, percent single family housing and median age. So we're going to use these three to sort of represent diversity or differences in the Kansas City region. So let's grab that with get census. We're going to use basically the same syntax, but in this case, we're going to pass a list of variables to the variables parameter. And we're going to specify two states, 20 and 29, and they can be comma separated here. And we'll grab then data for both Kansas and Missouri in one call. So let's jump back here, pull our data. We're calling it metrics. Again, we get it in a second, and we can do metrics.head. And so here's the structure of our data. We have these three variables, and we've got a GeoID column. I'm going to take an additional step here, and I'm going to, you'll notice how I kind of parse this out. I'm going to merge to I'm going to do a little method chaining here. I'm going to take my Kansas City census tracts. I'm going to merge to it my metrics on the GeoID column. I'm going to take a step here that is helpful for illustration. If this were sort of an applied workflow that we were doing at our job, we would need to take this more seriously. I'm filling in missing data using the fill in a method with a 0. So if something has a 0 for any of the values, excuse me, an NaN or a missing value for any of the values, I'm just putting a 0 in instead with the fill in a method. Is this a good or a bad decision? In some cases, it's fine because nobody lives there, so we can put in 0. In other cases, if it's just because the estimate was too small and it might not actually be 0, I may be making a mistake here. But I want to show this for purposes of illustration. And we want to avoid islands. So, for example, if I hadn't done this and I tried to build regions, I'm trying to build spatially contiguous regions, which means all the regions are connected. Well, in Kansas City, there is a census tract in Kansas City, Kansas, so on the Kansas side, that is entirely surrounded by industrial areas that have nobody living there. So it's literally a population island. And so if you remove missing data first, the regionalization algorithm can't solve because it doesn't know where to put that census tract that's surrounded by industrial areas that has no people. So we're just going to basically replace the missing data with 0s to skip over this for today. So I'm going to run that. Now we get to the fun part where we can play around with PySal. So to build regions, you have to define what contiguity is. Like, how do you know which census tracts are next to each other? We build what's called a spatial weights matrix, which is implemented in the libpysal package. We're going to import the weights module. And you'll notice here in weights, there are a bunch of submodules. So PySal is very hierarchical. The function that we need is called from data frame. And that belongs to inside of weights, we have contiguity and we have queen. And so what we're building is what's called a Queen's case spatial weights matrix, which means that we're considering any census tract to neighbor another census tract if any single point, so any vertex, is shared with another tract. And so we can go into this in much more detail. That's the nuts and bolts of it. What I just want to do is show you a visual representation of what that looks like. We're using the splot package to plot the contiguity weights. And I'm going to jump back over here and do that myself. So these connectivity, you see out here in the more rural part up here in Missouri. So this census tract, you can see which other tracts are considered to be neighbors. So it neighbors this tract, this tract, this tract, this tract, and this tract, because it shares at least one point, either a point or a line segment with the neighboring tracts. Obviously, it gets a lot more dense in urban Kansas City, but that gives you a visual representation of how neighborhood relationships are being defined. Once we do that, we can implement a regionalization algorithm. And there are actually several regionalization algorithms implemented in SPOpt. Some of which you get to specify the number of regions beforehand. We're using the Skater algorithm, which is the same one I use in my book, to do that. And in this one, you do specify the number of regions. Others, like MaxP, you don't specify the number of regions beforehand. So it really depends on kind of the solution that you need. The implementation of Skater, and I'm not going to get too much into the technical weeds here, but the implementation of Skater in PySal and SPOpt is so fast, and it's really, really great. You can read more about Skater in chapter 8 of my book. But what we do here is we specify a random number seed. That's going to be important for reproducibility of our findings. And we're going to specify an input data set, a geodata frame, a weights matrix. For Atter's name, we're going to give a list of variables, so a list of columns in our data set that we want to use to determine spatial attribute homogeneity. We're specifying all the variables that we requested with get census. N clusters. This is the number of regions to solve for. So we want 10 geographically and demographically coherent regions. And then floor is the minimum number of census tracts that we can have in a region. So we need each region to have at least 10 census tracts. So this is, you can think of as a spatial optimization problem. We need, where we have a bunch of constraints. We need to minimize the heterogeneity or maximize homogeneity amongst these variables. We need to solve for 10 geographically coherent and contiguous regions. And our minimum number of census tracts within each region has to be 10. It's a fairly complex problem to solve. But the beauty of this is the PySal team has already figured out how to do this for us. So I'm going to run this through. And frankly, the way I described it, that's a reasonably complicated optimization problem to solve, but it solves within 8 seconds. And so let's take a look at the results. I'm going to assign the labels from the solved model back to a new column called region, and I'll plot it. And here we see the results. Each color represents a geographically contiguous and demographically coherent region. And that's pretty interesting. Now, if you don't know much about Kansas City, and I've never lived in Kansas City, so I was born near there when I was little, but I've never actually lived there as an adult. You might not know what these regions are. So what do we do? Let's use the explore method. I am going to do KC metrics .explore, and I'm going to do column equals region, categorical equals true, tooltip equals false, pop-up equals true. All right. So what I'm doing here is I'm saying plot the region column, plot it as categorical, turn off the tooltip, allow for a pop-up. And now I have an interactive map that allows me to delve in more deeply. So here, as I zoom in, I can see, okay, Overland Park is one such region. Lenexa Mariam is one such region. We have kind of a Kansas City, Kansas region. We have an urban Kansas City region. We've got more of a couple suburban regions on the Missouri side. One kind of south suburban region, one north suburban region. And you can really kind of drill down and then maybe get a sense of these demographics. So if we look here, I can click on any of these and I can see what some of these values are. And I'm not aliasing in the tooltip. So this is a highly educated, pretty highly educated region that is mostly multifamily housing. So just as a reminder of what this is, 72% have a degree or higher, but only 22% is single family housing. And the median age is about 41.1. So we've got relatively high, this is high density, highly educated. If you go out, say, to the region out in sort of the south and east suburban, those numbers are pretty different. So educational attainment here, 36.9%. Still reasonably high, above average, but much lower than that urban Kansas City tract. 99.2% single family housing. So very different than the urban tract. And the median age is about 40.9. So you could click around and see some of these differences. Here's a younger area with a low educational attainment, but still mostly single family housing. So you can kind of get a sense of how this works. And regionalization and spatial optimization is pretty cool. I'm going to leave this up here. I got one question about the interactive mapping code, so you can go ahead and try that out for yourself. So let me just jump back to the slides real quick and close things out with the last slide before I come back here. Thank you so much for attending. For those of you who have stuck around the full 3 hours, frankly, over half of you did. That is much appreciated. I appreciate you taking time out of your busy schedules. Again, final plug, if you're interested in this stuff, pick up a copy of the book. Even if you're more of a Python user, there's a ton in there to look at. And thanks again to Bill, Jessica, Valencia, Dan, for putting all this together. I've really had a great time.
Well, Kyle, thank you very much. It's really us that really should be thanking you. This is a Herculean effort. 3 sessions, 3 3-hour sessions. Those of you who've been through all of it have gained so much information as we have, and we're so pleased to have Kyle with us. As we mentioned earlier, in a few weeks or a few days, we don't quite know when, but it'll be soon, we're going to have all of these webinars up, video webinars, the 3 3-hour webinars, the one looking at the 2021 ACS with R, the other one looking at mapping and spatial analysis of the 2020 ACS with R, and the one that you just heard today with Python. It'll be a huge thing for you to go back and review what you've heard. If you haven't looked at all 3 of them, you can go back and look at some of the earlier ones and certainly share them with your friends. And again, I want to put another plug for Kyle's book, Analyzing Census Data with Methods, Models, and Mapping with R, which you can get on Amazon and Routledge. And, you know, I think you'll get a lot out of it, especially since you've attended these surveys. So thank all of you. Kyle, everyone at the University of Michigan Social Science Data Analysis Network has helped the logistics of all of this, and certainly all of you participants who've come. Thank you very much, and we'll hope to continue this in the future, but you've got a lot to chew on right now. So good luck, and thank you again.
All right. Thanks, everyone. Appreciate it.